The lamp is dim and steady, and the day has finally put itself down. As you settle into your chair, let your shoulders lower with your breath, in and out, like small waves on a lake. You are safe here, warm and unhurried. Above the roof, the sky keeps an old, patient watch, and from that quiet distance comes a soft puzzle. James Webb has seen a hint that seems older than the Big Bang, a whisper that does not fit our clocks. We will not chase answers. We'll drift beside the question, letting it rock us toward rest. If this stillness eases you, a gentle like and subscribe helps this little harbor stay close. Close your eyes. Let the room dim to hush. We'll rest and listen together. For many decades, we carried a tidy picture. The Milky Way was about 100,000 light years wide. Quietly, the picture doubled. Our home is closer to 200,000 light years across, perhaps more. New tools, patient, precise, have brought this into view, and that larger shape touches many things. How we measure the universe, how we think about the future meeting with Andromeda, even how wide our search for neighbors might be. You may remember the textbook sketch, a neat spiral labeled with simple numbers. That number was not just a little off. It missed half the story. For years, scientists felt a tug of doubt. Pieces did not fit. Some stars at the rim moved too fast. Small companion galaxies circled farther out than expected. Mass totals never balanced. Then measurements began to line up data from Gaia, tracing stellar motions, quiet notes from radio telescopes, mapping hydrogen far from the bright disk, and new eyes like James Webb peering through dust. Different instruments, same pattern. The Milky Way reaches well beyond the line we once drew. The trouble is not carelessness. It is our address. We are measuring the house from a hallway inside it. Imagine standing in the middle of a city and trying to draw its border. Lights and buildings crowd your view. You cannot step outside to see the shape. Our sun sits in one spiral arm, about 26,000 light years from the center, with thick swaths of dust and gas in the way. For a long time, the method was simple. Look in every direction, mark where bright stars thin out, call that the edge. But a galaxy does not end like a plate. It fades. Stars trail outward in faint streams and clouds, and beyond the starlight lies something darker and wider. What changed the map were those streams, rivers of stars pulled from smaller galaxies the Milky Way swallowed long ago. They move like fossils in orbit, their paths shaped by the full gravity of our home. When researchers traced these gentle arcs, they found them far beyond the old boundary, 200,000 light years out, and still circling. It was as if we had been measuring a shadow and mistook it for the whole. This is more than a new number. It reshapes how we think about a galaxy's body and halo. It nudges the timing and geometry of our slow dance with Andromeda. It means the volume of space where life could hide around us is larger than we counted. And it leaves a quiet question hanging in the dark. If we were this wrong about our own home, what else might be larger, softer at the edges, different than the pictures we drew? Picture another scene. You are blindfolded in a desert and asked to map the sand. No GPS, no high view, only the grain beneath your feet and the wind on your skin. That is the puzzle of charting the Milky Way from inside. We sit on a small world around an ordinary star. Dust hides the center. With visible light, we glimpse maybe a modest slice of the whole. The rest reveals itself in radio waves, infrared glow, and silence. Looking outward helps. Andromeda sits far enough away that we can see it at once. Disk, arms, clusters, the gentle tilt. Measuring our own galaxy is more like trying to photograph your face without a mirror while standing in fog. Early astronomers did what they could. They watched Cepheid variables, stars that pulse like steady clocks, and they mapped globular clusters, ancient balls of stars that circle the core. Piece by careful piece, they built a map. Then came a shift. Use motion instead of light. Everything orbits the center stars. Gas, whole clusters. Speed tells you mass. Measure how fast something moves, and you learn how much gravity is pulling on it, which tells you how big the hidden structure must be. Yet the numbers were strange. At the outskirts, stars moved too quickly to be held by the visible matter alone. They should have drifted away. Something unseen was holding them close. We call it dark matter, not a glow, but a weight, an invisible halo wrapping the galaxy like a soft cocoon of gravity. Old measurements counted only the bright parts, stars, shining gas, glowing clouds, and left out this quiet scaffold. Modern tools changed that. Gaia maps the motions of more than 1 billion stars with exquisite care. Radio arrays trace cold hydrogen gas far into the outer reaches. Infrared eyes look through dust and bring hidden regions into view. Each method adds a layer, and together they reveal a larger, gentler boundary. Even our small companion galaxies serve as test weights, their paths curving through the Milky Way's wider embrace, telling us where the mass truly lies. Around our galaxy drift many small companions, the large and small Magellanic Clouds, the Sagittarius Dwarf, and others dimmer still. They move the way leaves move on a slow river, their paths set by all our mass together, the bright and the unseen. When astronomers traced these orbits and added them to the growing map, the picture grew hushed and large. The Milky Way is not a modest spiral. It is a heavyweight, wide and deep, roughly twice the width we taught, with far more mass than we once counted. To learn this, scientists followed quieter clues. Stellar streams sound dramatic, yet they are gentle fossils of old encounters. Small galaxies that wandered too close and were pulled apart, their stars stretched into pale ribbons. Those stars did not vanish. They kept circling, writing long, thin lines across the halo. Some streams are wider than the whole path Earth takes around the Sunday. Others carry thousands of stars moving as one, like a flock keeping shape across years. For a long time, we looked past them, treating them as background. They turned out to be the best rulers we have. A stream moves where gravity tells it to move. Follow the curve of the ribbon, and you feel the pull of the whole galaxy. No guesses, just motion. One of the most famous is the Sagittarius stream. It wraps around the Milky Way again and again, like soft ribbon around a gift, and it reaches far beyond the old edge we drew. Then came a thread called GD1, a narrow river in the outer halo. Its bend did not fit the pull of the visible stars alone. The curve asked for more weight than the bright disk could supply. Nothing was broken in physics. Something was missing from our eyes. Dark matter that does not glow, was shaping those paths. We cannot see this material directly, but we can see what it does. It holds stars in faster orbits. It keeps galaxies from flying apart, and it bends the travel of light that passes by. The stream showed its hand the way invisible ink shows up under a lamp. As maps improved, more streams appeared in places we used to call between galaxies, regions we thought were empty. They were not empty at all. The Milky Way's pull reached there, steady and patient. The orphan stream was a puzzle for years, so far out that some wondered if it belonged to another system. Careful measurements drew it back to us. Each new stream set the boundary a little farther out, 5,000 light years here, 10,000 there. Numbers climbed past 120,000, then 150, then 180. The pattern kept saying the same quiet thing. Our galaxy extends to about 200,000 light years, and the influence of its mass reaches beyond that. By then, the question changed. It was less, how big is the Milky Way? And more, how did we live with a smaller picture for so long? Part of the answer is simple. We only see the bright bones. Most of the body is hidden. Close to 90% of our galaxy's mass is invisible to our eyes. Dark matter is not a guess tossed into the dark. It is measured through its effects, through speeds that are too high for starlight alone, through arcs of light that bend as they pass, through the calm obedience of streams. In our galaxy, the unseen does more than add weight. It sets the frame. Imagine a skyscraper where you only see the windows at night, glowing squares against a black sky. The steel beams that hold everything up are there, but the light does not show them. Our stars are the windows. Dark matter is the frame. Many studies suggest the invisible outweighs the visible by something like 10 to 1. For every star you can point to, there is far more mass nearby that your eyes cannot catch. That mass forms a halo round, spread out and reaching well beyond the bright spiral. Old measurements paid attention to the shining parts, the arms, the core, the obvious shape. The starlight thinned near 100,000 light years, and we called that the edge. Yet the halo keeps going, faint and patient. Some ways of measuring it, including how much our mass bends passing light, a method called gravitational lensing, hint that the halo's wispy outer regions could extend toward 400,000 light years. Where to draw the line becomes a softer question. Galaxies do not end like a cliff. They fade. The density of dark matter lowers, little by little, until it blends with the broader sea of space. So, astronomers use a practical boundary called the virial radius. Think of it as the distance within which the galaxy's gravity still keeps a family together. Inside that sphere, stars, gas, clusters, and streams share the same long conversation and remain bound. Outside, the pull loosens, and space is truly between homes. For the Milky Way, that working boundary sits around 200 to 250,000 light years, about twice the old picture. All of this folds into a calmer truth about structure. Galaxies are not islands of starlight floating in emptiness. They are enormous halos of hidden mass with a bright center sprinkled through. The luminous part is decoration, the invisible part is the scaffolding. And if this is true for us, it is true for others. The universe grows heavier and quieter in our minds, and our maps stretch out to match. As you breathe, imagine that round, gentle halo holding us, streams curving like thin paths of dew, small companion galaxies drifting in wide circles. The house is larger than we knew, and it holds. Our galaxy is not alone. Dozens of smaller companions move around us like moons around a planet. The large Magellanic Cloud, the small Magellanic Cloud, and quieter dwarfs like Sagittarius, Draco, and Ursa Minor. From the south, the large Magellanic Cloud appears as a soft smudge, and inside that blur live about 30 billion stars. The small Magellanic Cloud nearby holds several billion more. For a long time, we treated these companions as passing neighbors. Careful measurements told a different story. They are not drifting by. They are bound to us, moving inside the Milky Way's wide embrace. When something orbits, its speed and distance whisper the mass that holds it. The large Magellanic Cloud, sits roughly 160,000 light years out and takes about 1.5 billion years to circle once. To keep a companion that large and that far moving on such a slow loop, our galaxy must be heavy, heavier than the old estimates allowed. Astronomers traced many satellites and found the same pattern: paths farther out, speeds a little too quick for a modest spiral. The conclusion was quiet and firm. The Milky Way is bigger and weightier than we thought. The clearest rulers came from tidal streams. When a small galaxy swings in too close, our gravity stretches it thin. Stars peel away in long trails that wrap around the sky like pale ribbons. The Sagittarius dwarf is being unspooled like this now, its stars arcing across the darkness. These tidal tails act like test weights in a calm laboratory. Where they curve, the pull is strong. Where they fade, the pull eases. Map enough ribbons, and you begin to feel the edge of the house. The surprise was how far those lines ran past 150,000 light years, past 200,000 inches, some directions hinting at material even farther out. The satellites and the scars they leave kept pointing to the same truth. The Milky Way is vast. A change in size ripples outward. If our halo is this wide, the space between us and Andromeda shrinks a little in practical terms. Each galaxy's reach extends farther, so the long, slow meeting between them inches forward on the cosmic calendar. In this retelling, every companion becomes a data point, every orbit a gentle measurement. Together they paint not a medium spiral, but a giant quiet on the outside, deep and heavy within. And the picture is still coming into focus. Some satellites circle so far out that we are only now finding them in the faintest patterns of stars. With each new dwarf added to the map, the boundary breathes outward by a few thousand light years more. Numbers this large slip through the fingers. 200,000 light years across is easy to say and hard to feel. A kinder way to hold it. Even at the speed of light, the fastest anything can move, it would take about 200,000 years to cross our galaxy from side to side. The light that leaves one edge arrives after whole chapters of human history have turned. Much of the glow we see from the far rim began its journey before modern humans walked the Earth, before the older branches of our family took shape. The scale drifts past daily sense, and that is all right. Let it be big. Let it be soft at the edges. Yet size is not only a curiosity, it touches something close. Double the width and the volume swells in 3 dimensions. A galaxy twice as wide holds about 8 times the space. More room means more stars, more worlds, more small moons with hidden seas. Old maps gave counts near 200 billion stars. Newer ones lean toward 400 billion, perhaps more. Many of those suns likely host planets. Some of those planets may carry water under ice, or clouds that rain on silent plains, or warm tides tugged by nearby moons. The number of possible homes climbs with the size of the roof. Breathe with that thought. The satellites circle in slow, patient arcs. Their streams thread the darkness like silver paths after rain. Far beyond the bright spiral, the Milky Way's pull still holds a wide, unseen hand steadying the dance. Inside it, our small world turns, and the night becomes a softer, larger room. If life is rare, say 1 in a billion star systems, our larger map quietly adds hundreds of billions more chances. If minds like ours look out from some distant shore, the odds of meeting them or them finding us rise a little. Size also touches our timeline. Andromeda is drifting toward us at roughly 70 miles each second. When galaxies meet, They do not crash like cars. They pass through, they pull, they merge. Stars are so far apart that almost none collide, yet gravity stirs the whole scene and the shapes change. Older estimates place the first close pass around 4.5 billion years from now. A heavier, wider Milky Way extends its reach, so the gentle tug begins sooner, perhaps near 4 billion years, maybe a bit less. If our line continues that long, your far-off descendants would watch Andromeda swell in the night, growing larger and brighter until it hangs across half the sky, a pale river of stars crossing our own. The two disks would loop and weave, spirals braiding before they settle into a single, rounder form. 200,000 light years is not just a number. It is the stage on which every human story unfolded in a very small corner, and that stage is larger than we thought. This approach is not a guess. It is measured. The timeline shifts because gravity begins with the halos, the wide envelopes of dark matter that stretch far beyond the bright spirals. When those halos touch, the encounter has begun, even if no one can see it with ordinary light. Think of two people walking toward each other. If both are bigger than you thought, they meet sooner. Some new models place the first deep interaction under 4 billion years from now, perhaps 3.5. The exact date will sharpen as measurements improve, but the direction is clear: bigger halos, earlier contact. Here is how such a meeting unfolds. First, the invisible halos mingle, and the pull from two centers reaches across the same stars. Orbits wobble. A few stars are tossed into the dark between galaxies. Others drift inward. Later, the bright disks pass through each other like two misty clouds. Direct star-to-star collisions remain rare, yet gas clouds feel the squeeze. They compress, and new stars spark in wide arcs. The galaxies sweep past, turn, and pass again. With each loop, their arms fray. Tidal forces pull streamers of stars into long, soft trails. After many passes, perhaps 1 billion years, the pair settles into one great elliptical system. Astronomers even have a nickname for this future home: Milkometa. What happens to us? The sun lives far from the Milky Way's crowded core, so it will likely ride through without a direct hit. Earth could keep a similar path, drift outward, or be nudged into a longer, colder loop. A slim chance even sends it free into intergalactic space. The odds favor survival of the system, yet the sun's own clock runs down. It has roughly 5 billion years of fuel, so it will shine through the early phases of the encounter, but not forever. A larger Milky Way moves the opening act a little earlier, which means the first changes in the sky arrive while the sun still burns. And somewhere, there is a quieter possibility. If Andromeda is also larger than we thought, the halos may already be brushing in the dark. On cosmic calendars, 4 billion years is tomorrow, and tomorrow has stepped a little closer. Mass is the heart of the story. The Milky Way has gained weight on our ledgers, not by adding matter overnight, but by us finally counting what was always there. Old totals hovered around 1.5 trillion times the sun's mass. New lines of evidence lift that toward 4 trillion, perhaps more. A solar mass sounds abstract, so hold it this way. The sun contains almost everything in our solar system. The planets together are only a tiny sliver by comparison. Now multiply that single sun by trillions upon trillions, and you begin to feel the quiet strength of our galaxy. Where did the extra come from? Most of it is dark matter, which does not glow but pulls. Early work leaned on rotation curves, measuring how fast stars circle in the inner regions and inferring mass from that speed. Those measures were easiest where starlight is rich, and they undercounted the far halo where the invisible dominates. New methods reached farther. The orbits of satellite galaxies gave direct mass checks at great distances. Long, stellar streams traced the shape of the gravitational field like silk threads on the wind. Large simulations compared our motions to thousands of mock galaxies with known masses. Different tools, same answer: a heavyweight Milky Way. Heavier means a stronger hold. We can keep more dwarfs in orbit, peel stars from small passers-by, and tug on the local group with a firmer hand. Andromeda, once assumed to be the larger sibling, now looks comparable in mass, two giants drawing near. Weight also remembers the past. Galaxies grow by eating smaller ones. The more massive you are, the more meals you have had. The halo streams are the quiet record of that history, each one a path left by a galaxy pulled apart. Even now, the Sagittarius dwarf is being thinned to lace, its stars poured into our disk and halo until only patterns in the data remain to whisper its name. Most of what holds us together is invisible, yet its gentleness is steady. Let that thought soften the breath. The future meeting with Andromeda is far beyond any single life, yet it is woven into the same sky that watches you tonight. Larger maps do not make the night harsher, they give it room. Somewhere within a halo of hidden mass, on a small world warmed by a steady star, you are listening, and the universe is patient. Most of what holds our world together is hidden. Close to 90% of everything around us does not shine, cannot be touched, and does not speak in light. We move through it without feeling a thing, like swimming in water so clear you forget it is there. Our home carries roughly 4 trillion times the sun's mass, and most of that weight is invisible. The starlit disk is only the bright skin. Beyond it, the galaxy keeps going, far past where the glow thins, into a wide hush of dark matter. Astronomers call this round envelope the dark matter halo. It is not a trim border, it is the main structure, the quiet frame holding the Milky Way together. A careful, conservative map places the bound region, the virial radius, near 250,000 light-years from the center. Some models push farther, 400,000, 600,000, even toward 1 million light-years in the faint outskirts. At that scale, the diameter reaches about 2 million light-years, roughly 20 times the old textbook figure of 100,000 light-years across. Set that beside Andromeda, about 2.5 million light-years away. If our halo stretched to 1 million light-years, and Andromeda's did too, the truly empty gap between them would be only about 500,000 light-years. The two halos could already be brushing, like two cool clouds mingling long before the rain appears. We do not see the halo directly. Dark matter does not glow or block light. It only tugs through gravity, so scientists read its shape by indirect signs. The paths of satellite galaxies tell where the pull is strong. Gravitational lensing tiny bends in the roots of faraway light shows where space curves. Computer models of how galaxies grow predict where invisible mass gathers and thins. Put the clues together, and you get a round, diffuse halo, denser near the center, fading like fog toward the edges, with no hard wall, only a slow drift into the wider dark. For practical work, the virial radius marks the sphere where the Milky Way's gravity keeps its family bound. Outside that, space belongs more to the in-between. If the halo truly reaches on the order of 1 million light-years, then a large share of the local group sits within our gentle sphere of influence. Ours would be a quiet empire of gravity, a a superstructure with the bright galaxy nestled like a seed within the fruit. The halo answers old puzzles. Stars far from the center move faster than starlight alone can hold them. The halo's gravity keeps them in their paths. Whole galaxies spin without flying apart because that extra mass is there. Light from distant objects bends a little more than the visible matter can explain. The halo adds the missing curve. Stranger still, you are inside this structure right now. Dark matter streams through Earth all the time, with particles moving hundreds of miles per second, passing through rock, oceans, and through you trillions every second without leaving a mark. Deep underground, quiet detectors wait for a rare tap on an atom. So far, the instruments remain still, which could mean the particles are rarer or quieter than we expected, or that our nets are the wrong shape. Spin brings us to another quiet surprise. In our solar system, orbits slow with distance. Mercury whips around fast. Earth takes a year. Neptune needs more than a century. Newton and Kepler showed why. Farther out means weaker gravity and slower motion. By that rule, stars far from the galactic center should move slower than stars near the middle. When astronomers measure the speeds, the curve should slope downward. Instead, it stays flat. Stars at the edge circle almost as quickly as stars closer in. That flat line is the strong hint that extra mass dark matter extends well beyond the bright disk. Even after adding the halo, details keep us awake. Some stars in the outer regions race at about 130 to 150 miles per second, close to the speed needed to escape entirely. They skirt the edge of freedom and still remain bound. This escape velocity problem suggests we may still be undercounting mass, or that the halo is shaped differently than our simple picture, perhaps denser in the outskirts, perhaps lumpy with unseen clumps. History can help explain it. Recent mergers can fling stars onto fast, long orbits. We are watching one such meal now, the Sagittarius dwarf being pulled apart, its stars scattered into the halo with extra energy. After enough time, those stars will blend in, looking like any other swift halo stars. Curiously, some stars do the opposite. They drift slower than their neighborhoods suggest, as if moving through a thicker syrup of gravity. Those outliers are rare and puzzling. This is the proving ground for dark matter ideas. Different models sketch different rotation curves. Warm dark matter tends to smooth the outskirts. Cold dark matter makes more small clumps. Particles that nudge each other, self-interacting dark matter, can soften the core. Right now, cold dark matter gives the best broad match, but not a perfect one. The mismatches are small, stubborn, and interesting, the kind that could point to better measurements, richer models, or new physics whispering at the edges. A larger Milky Way makes these tests sharper. More volume means more stars to weigh, more streams to trace, more odd velocities to explain. The map grew. The questions became clearer. Let the thoughts settle gently. We live inside a wide, invisible halo that steadies the galaxy and shapes the sky, and we are still learning its lines, one orbit, one faint stream, one careful measurement at a time. Astronomers still argue about how many main arms our galaxy has. For years, the neat answer was 4: Scutum Centaurus, Norma, Cygnus, Perseus, with Sagittarius often listed close by. Picture each arm as a slow river of stars, gas, and dust sliding outward from the bright core, a place where new stars light up like towns along a highway at night. Those were the lines we drew in textbooks, because they were bright, dense, and simple to see. Then better eyes arrived. Infrared instruments looked through dust the way warm light shines through fog. Radio dishes traced cold hydrogen, the raw fuel for stars. Space telescopes rose above the blur of air and weather. Bit by bit, hidden features stepped forward. One of the first surprises was called the Far 3 kiloparsec arm, a whole spiral lane tucked behind the center. A kiloparsec is about 3,000 light years. Optical views missed it because the core blocks our sight, but infrared slid between dust grains, and there it was, an arm thousands of light years long, right where the glare once made us blind. Hints piled up. The local arm, the lane that holds our sun, might be more than a short spur. New maps suggest it ties into larger pieces farther out, like finding out the side street you live on is actually part of a major road. The outer arm brought its own puzzle. It sits at the faint edge of what we can see. So many thought it was a scatter of lonely stars with no real order. Careful mapping showed patterns after all organized spirals extending into places we once labeled empty. A bigger Milky Way gives more room for structure, and in that room, arms can stretch farther and new branches can grow. Underneath all of this sits a deeper mystery. No one fully agrees on how spiral arms form or last. Stars do not all move at the same speed. Closer to the center, orbits are faster. Farther out, orbits are slower. If arms were made only of the same stars staying in the same place, they would wind up and smear out in just a few turns, like cream stirred into coffee until the swirl vanishes. Yet arms persist for billions of years. That led to the idea of density waves, not a permanent string of the same stars, but a traveling pattern where stars and gas bunch up for a while and then pass through, like cars moving through a traffic jam while the jam itself seems to sit in place. The math can make this work, but the sky keeps handing us exceptions. Some arms hold more young stars than the simplest wave picture allows. Other places show gaps where models say stars should be. The outer arm may even be too massive and too clean to be only a wave. It could be real material pulled and shaped by an old encounter with a passing galaxy. The sharper the map, the messier the picture gets in a good way. The Gaia spacecraft has measured positions and motions for well over 1 billion stars with steady patience. With that detail, the arms break into substructure, small branches, side spurs, bridges, and holes. The grand pinwheel is less like a smooth spiral and more like tree limbs and twigs, growing and twisting in many directions at once. That has led some researchers to say the Milky Way is not a strict grand design spiral with a few perfect arms, but closer to a flocculent spiral, patchy, clumpy, and variable, where arms can start, fade, and restart. Different surveys see different pieces depending on what they measure. Bright newborn stars, older red giants, glowing gas, cold hydrogen, dust lanes. No wonder arm counts do not match. Each tool draws a different layer of the same living sketch. The shared lesson is simple and humbling. Our galaxy is more intricate than the four-arm cartoon we carried for decades. We missed whole structures in our own backyard, not because we were careless, but because dust is thick, distances are vast, and our point of view is stuck inside one arm, looking across a crowded city of stars. If great lanes of the Milky Way can hide in plain sight, other features may be waiting too. Shells from ancient mergers, faint rings, or ripples in the disk from a close pass long ago, each one quiet until the right instrument and method find it. Now try to draw a line around the galaxy. It sounds tidy. It is anything but. Galaxies are not countries with fences and signs. There is no now leaving the Milky Way marker. Starlight thins slowly. A few stragglers wander well beyond the bright disk. Where does ours end and not ours begin? That is not just poetry, it is a practical headache. To compare galaxies, to count their stars, to time their meetings, astronomers need working borders. The universe, for its part, refuses to snap to our rulers. Several stand-ins exist, each useful and each flawed. The optical radius marks where the bright disk fades below easy detection. For the Milky Way, that gives a tidy number near 100,000 light-years, the classic textbook width. But that leaves out dim stars, tiny dwarfs, and the ragged halo. It is like measuring a city by counting only skyscrapers while ignoring the neighborhoods that cover most of the map. A more physical choice is the virial radius. Think of it as the distance within which the galaxy's gravity keeps things bound as a family. Inside, stars and gas share the same long orbit around the center. Outside, objects can drift their own way. For the Milky Way, many studies place this boundary around 200 to 250,000 light-years, far larger than the bright disk. Better, but not clean. Some stars beyond that radius still move with us, and may have formed here. Should a star that shares our motion but lives just outside the line count as Milky Way or not? The virial rule says no. Common sense says maybe. Go one step farther and ask about the dark matter halo. If the halo fades out only slowly and may reach hundreds of thousands of light years, perhaps toward 1,000,000 in the wispy outskirts, does that set the true edge? Most astronomers say no. The halo's outer parts are so diffuse that drawing a firm line feels arbitrary, the way it is arbitrary to say where Earth's atmosphere ends. Technically, air stretches for thousands of miles. Practically, for most uses, it is gone after the first 100 miles. The useful boundary depends on the question. Outflows make the border softer still. The Milky Way breathes. Supernovae crack open and push gas outward. Hot winds from clusters of young stars shove material into the halo. Some of that gas will cool and rain back down over millions of years, feeding new stars. Some will drift off for good, fading into the space between galaxies. At what point does that gas stop being ours and become part of the intergalactic medium? There is no single answer. The Magellanic Stream adds another thread. The large and small Magellanic Clouds, the bright satellite galaxies in the southern sky, are losing gas as they orbit us. That gas trails behind them in a ribbon that crosses great swaths of sky. Is that ribbon Milky Way gas because it now moves in our field? Magellanic because it came from them? Or neither because it lives between? You can defend all three views, depending on which measure origin, motion, or location you care about most. Look outward, and the problem meets us from the other side. Andromeda's dark halo likely stretches far, perhaps far enough that our two halos already overlap. If dark matter halos mingle, where does one galaxy end and the other begin? The space in between becomes a shared zone, co-owned by gravity. That is not a mere word game. Mass estimates, size rankings, and even the start date of our slow merger depend on the boundary you choose. If the halos are touching now, the first stage of the Milky Way Andromeda encounter has already begun in the dark, long before the bright disks feel the tug. By one sensible rule, we are living inside the opening chapter. So most astronomers settle on practical layers. The star-forming disk ends where young clusters fade out. The bound halo is counted to the virial radius. The dark matter extends as far as models and lensing data suggest. With a soft tail, each layer answers a different kind of question. None pretends to be the one true edge. The honest summary is simple. The Milky Way is not a sharp object. it is a region. It is a zone of influence with a dense core, a structured middle, and a diffuse edge that blends into what lies beyond. For today, a working number of about 200,000 light-years captures the reach of our galaxy's bright and gently bound parts, while the virial radius pushes that reach closer to 250,000 light-years, and the dark halo breathes outward still farther. Ask again in 10 years, and the figures may shift, because our tools will be sharper and our maps deeper. That is not failure. It is how a live science moves, by adding detail, revising friendly diagrams, and learning to see what the night was showing us all along. The picture that emerges is both complex and calming. Arms that may be 4, 5, or 6 fold into one another, branch, and fade. Waves of star birth move like traffic patterns across a vast city. Borders melt from bright streets into quiet neighborhoods, and then into fields. Our galaxy is not a hard shell. It is a living district of gravity, one that overlaps with others, trades gas with its satellites, and keeps time with a partner we can already feel in the dark. We measure what we can, mark what is useful, and accept that the edges of things in the universe are more like twilight than like walls. At the far edge of our galaxy, some stars move with remarkable speed. Many cruise near 130 miles per second, others near 150, and a few brush 200. By simple rules, they should slip free into intergalactic space. They do not. Something holds them in a delicate balance. Astronomers call them high-velocity halo stars, quick and faint, but still bound different from hypervelocity stars, which reach speeds high enough to escape entirely. They were hard to spot, distant, dim, scattered across an enormous volume like fireflies at the edge of a field. Patience changed that. Surveys such as Gaia measured the positions and motions of millions upon millions of stars with exquisite care. From those tiny shifts on the sky, you can recover true speeds. A few objects raised quiet alarms at once. One traveler in the outer halo moves at about 198 miles per second, where the local escape speed is roughly 200. That star is within 2 miles per second of leaving forever like a rocket barely held by Earth's pull, a whisper of extra push away from the dark between galaxies. Why do so many stars live so near the rim of freedom? Chance alone cannot pile them up there. Something set them on those paths with just enough energy to skim the boundary. One answer lies in our past meals. When the Milky Way swallowed smaller galaxies, it didn't simply add stars like beads to a bowl. The encounters stirred the whole system, injecting energy into orbits. Some stars from the falling dwarf gained great speed. A portion escaped outright. Many settled into long, fast, barely bound loops. We are watching this process in real time with the Sagittarius dwarf. Its stars are being teased into streams, flung wide through the halo at high velocities. Give it 1 billion years, and they'll be indistinguishable from other halo stars. Quick, ancient, and hard to trace back to their source. Another route to speed comes from three-body dances. In dense clusters, 2 stars passing near a third object can exchange energy in a brief, intricate pull. One star may be kicked outward with a burst of motion, ejected from the cluster into the greater galaxy. Most of those sprinters either slow and settle or shoot all the way free. A smaller number land in that narrow band just below escape speed, circling the halo like skaters hugging the lip of a rink. Black holes add their own drama. A star that wanders too close to a massive black hole can be slingshotted to extraordinary speeds. Our central black hole weighs about 4 million suns. Anything that strays near risks being swallowed or hurled away. We have found true hypervelocity stars rushing out of the Milky Way at over 400 miles per second, and many of their paths trace back toward the center. Some were likely members of binary pairs. The whole captured one partner and flung the other outward. Yet the barely bound stars present a different pattern. They live far in the halo, not near the core, and their speeds, though high, are not extreme. They look comfortable at the edge of the Milky Way's gravity well, like swimmers hovering where the current meets the open sea. That edge may not be smooth. One idea suggests the dark matter halo is lumpy and layered, not a perfect sphere of gentle fade. If the halo carries subtle overdensities, clumps, shells, or ripples, those shapes could create preferred orbits where high speeds remain stable. Stars would settle into these resonant paths naturally, spending long eras moving fast without drifting away. If that is true, we should see patterns, groups of high-velocity stars sharing similar distances and directions, traveling together like loose schools of fish. Some surveys hint at the small clusters and streams showing common motion. Others see more scatter. The data are still prickly and incomplete, and the halo is a large, dim room to map. Even with the uncertainties, a quiet picture emerges. The galaxy's outskirts are wilder than simple models promised. The boundary between bound and unbound is thin, often a difference of just a few miles per second. If the Milky Way is larger than we once believed, there is simply more frontier, more stars living in that marginal zone, more chances to test where gravity yields. Understanding why they stay tells us about the shape of the dark matter around us, about the imprints of old mergers, and about how gravity behaves on the grandest scales we can study from home. And our home is not special. If we mismeasured the Milky Way, we likely mismeasured others, too. That realization sends astronomers back through their catalogs, because galaxies are the landmarks we use to understand the universe itself, how matter spreads out, how structure grows, how the tug of gravity and the push we call dark energy share the stage. If many galaxies are larger and heavier than the old map suggested, then interactions change as well. Bigger systems strip stars more easily from their neighbors, gather satellites more tightly, assemble clusters more efficiently, and seed different patterns in the cosmic web. Size bleeds into distance, and distance holds up much of cosmology. Some galaxy properties serve as distance rulers, standardizable patterns that link how bright something should be to how bright it appears. If a typical galaxy is larger or more extended than assumed, its light profile and total output can shift, and with them, the inferred distance. Small changes ripple outward. Distances feed into our estimates of the universe's expansion, which in turn shape our models of dark energy. A systematic bias in galaxy size can quietly tug on each rung of the distance ladder, from local groups to far clusters. So the surveys are being read again with gentler, wider eyes. The Sloan Digital Sky Survey, the 2-micron All-Sky Survey, and others are being revisited with new techniques that fold in halos, satellites, and stellar streams where those can be measured. Early looks suggest a consistent trend. Many galaxies appear larger than their classic figures, some by half again, some by nearly a factor of 2. Andromeda grows, Triangulum grows. If that holds in our neighborhood, it likely holds farther out, too. The web of galaxies could be denser than we assumed, its strands thicker, its nodes heavier with dark matter. None of this erases what works. The laws guiding planets around the sun still guide stars around a center, but the details get richer when the scaffolding of dark matter is counted honestly, and when history mergers, tides, and slingshots leaves fingerprints on the speeds we measure. A larger Milky Way sharpens the tests rather than breaking them. With more volume to explore, we find more fast stars, more slow outliers, more streams that curve in telling ways. Each one is a small piece of a longer, patient puzzle. Hold the image softly. A wide, faint halo with a luminous disk set inside. At the edges, stars moving briskly, almost free yet still returning. Here and there, a knot of dark matter shaping a lane where speed can live. Farther in, scars from past meals stretch like gauze tidal streams, tracing invisible contours. Across the local group, other galaxies wear similar halos and carry similar quirks. Our maps breathe outward, and the numbers change, and with them, our understanding of what binds the night. None of this needs to be loud, to be profound. A star at 198 miles per second, held back by 2, says as much about our galaxy as any bright nebula. It tells us the Milky Way's hand is steady, that its reach is wider than the light suggests, and that the structure wrapping us is real, even if it stays unseen. The more carefully we weigh these fast travelers, the more clearly we trace the frame that holds the sky. When the balance between dark matter and normal matter shifts, the story of how galaxies grow shifts with it. Ratios are not just numbers. They set the rules for assembly, the pace of star birth, the shape of halos, the weight of clusters. Change that balance and our predictions for the universe's past begin to move. Some long-standing puzzles may soften under this new light. One is the missing satellite problem. Computer models say a large galaxy like ours should host hundreds of small companions, yet we see only a few dozen. If our galaxy is wider and heavier than we assumed, its reach stretches farther. Those missing dwarfs might be out there after all, circling in the far quiet, where the night is thin and our surveys have only begun to look. Another thread follows the way galaxies spin. Many show the same flat rotation curves as the Milky Way stars at the edge, moving almost as fast as those closer in. Dark matter was first proposed to explain this, to supply the extra pull the starlight cannot. If galaxies are larger, their dark halos also extend farther, and those flat curves start to sit more naturally in the models. The physics fits a little better, as if a map has been unfolded to its true size and the roads line up at last. Yet recounting the universe has a price. Bigger galaxies leave less empty space between them. The cosmic neighborhood becomes more crowded. Encounters happen more often. Gentle pulls begin earlier. In clusters, great gatherings of galaxies bound together, interactions grow more tangled. Mass estimates shift. The shapes of the dark matter webs holding those clusters must be recalculated. Even the earliest times feel the tug. We read the history of the young universe by watching very distant galaxies, tiny smudges whose light set out billions of years ago. If those early galaxies were larger than we measured, then structure rose more quickly than we thought, and the universe reached a mature pattern sooner. The implications ripple through many corners of astronomy. How stars are distributed by age and mass, how galactic shapes emerge and fade, how central black holes grow and flare. When size changes, everything that depends on size must be weighed again. So the work begins anew, gently and thoroughly, counting galaxies, weighing clusters, redrawing edges with better instruments and deeper catalogs. The picture that comes back is larger, denser, and more intricate. The Milky Way was simply the first domino. Once it tipped, the rest began to move in line, and the pattern that spreads out is a web with thicker threads and closer knots. Amid these changes sits a quieter shift with practical consequences. The true balance point of our galaxy is not exactly where we put it. Every system has a center of mass, the point where all the weight averages out. For a yardstick, it is the middle. For Earth and Moon, it lies inside Earth, but not at its center, because the Moon pulls. In a galaxy, it is the place around which orbits truly curve. We assumed that point sat squarely at the visible core, where starlight is crowded and the supermassive black hole rests. That seemed natural, but it leaves out the halo, and the halo does not sit as a tight knot at the center. Dark matter forms a great diffuse cloud around the disk, not perfectly smooth, thicker in some directions, thinner in others. Count that mass honestly, and the balance point slides. The shift is not dramatic by the measure of the whole galaxy, hundreds of light years, perhaps 1,000, but in human terms it is enormous, farther than the gulf to our nearest star. It matters because gravity does not care about appearances. Stars, gas, and companion galaxies all respond to the real balance point, not to the place that looks bright. The orbits we calculate depend on where that true center sits. Measuring this offset is hard work. You need precise speeds for stars across the disk and into the halo. You need a careful picture of how the dark matter is spread. You need simulations that stitch the pieces together into one gravitational field. Only recently have our tools been tender and exact enough to try. The Gaia spacecraft provided the leap. Positions and motions for over 1 billion stars, measured with the steadiness of a metronome. Feed that river of data into models that include a lumpy halo and the balance point slides off the glare of the visible core. It does not coincide perfectly with the supermassive black hole. That small mismatch reaches into everyday galactic bookkeeping. Our solar system takes about 230 million years to circle the galaxy, a single galactic year. If the center of mass is slightly offset, the path we trace and the time we take will shift a little faster or slower by a small fraction. It also nudges the way we model the whole disk. For simplicity, many simulations assume perfect symmetry, a core at the exact center, a halo wrapped neatly around it. Reality remembers its history. The Milky Way grew by eating smaller galaxies. Those meals left scars, faint shells of stars, ripples in the disk, and off-center lumps of dark matter that bias the balance point. The Sagittarius dwarf, now being pulled apart, adds its own small weight to the ledger. Over millions of years, the center of mass can drift, almost like a buoy bobbing as small waves pass. Some researchers even suggest the balance point oscillates as new material falls in and slowly blends. The galaxy is not a rigid wheel. It is a living system, always adjusting. That leads to a gentle question about the black hole itself. If the center of mass has wandered, why does the black hole appear to sit at the luminous center? One answer is age. The hole likely formed when the Milky Way was smaller and more symmetric, and as the outer mass grew and shifted, the black hole stayed near the densest brightness peak. 4 million suns worth of mass has inertia. You do not move such an anchor easily. Another answer is patience. Over long stretches of time, the system may relax, the halo smooths, the scars of mergers soften, and the balance point drifts back toward the core. Even if the offset endures, the black hole remains close to the region with the deepest potential, where gas funnels in and stars crowd, so it still acts as the engine of the central neighborhood. None of this throws the night into chaos. It tunes the details. A slightly different balance point refines the tracks of stars and satellites, improves the alignment between models and measurements, and makes our long-term predictions a little steadier. Layer that onto the larger picture, bigger halos, broader galaxies, earlier encounters, and a consistent theme emerges. The cosmos keeps its laws, but the shapes those laws draw are richer than the simple diagrams we learned. Ratios shift, centers slide, edges blur, and the system holds together all the same. As you follow the thought, you can imagine the galaxy as a slow wheel turning in the dark, its weight spread not only in the bright streets of the disk, but also in a wide, unseen hush around it. The true balance point is not a nail hammered at the center. It is a quiet average of everything that is there, seen and unseen, near and far. Our measurements are finally sensitive enough to find it and to watch it move. That movement tells us the Milky Way is still growing, still settling, still shaped by the gentle pull of things we barely see. And each careful correction ratios revised, halos extended, centers adjusted brings the map closer to the landscape the night has always held. For now, in this moment of the galaxy's long life, the balance point sits a little off-center. The Milky Way turns around a spot that is not quite where we expected. As our map grew, that point drifted small by cosmic standards, huge by ours, and we are only beginning to learn what the shift changes. Collisions between galaxies are not loud or sudden. There are no fireballs racing across the sky, no crashes you could hear. What unfolds is a slow ballet of gravity that lasts hundreds of millions of years, yet size changes the choreography. A larger galaxy meets and merges differently than a small one. The rules stay the same, the outcomes don't. When two smaller galaxies meet, the dance can finish in a few 100 million years, perhaps 1 billion. They sweep past, stir each other, and settle. But when giants like the Milky Way and Andromeda approach, the story stretches. Greater mass means a deeper pull, and that deeper pull makes the motions more tangled. First contact happens in the dark, when the halos touch. Those wide, faint envelopes of dark matter reach far beyond the bright disks. Long before starlight overlaps, the halos mingle. Dark matter passes through dark matter without colliding, but gravity wakes up everywhere. Stars begin to feel two centers at once. Some orbits wobble, some loosen. A bit of quiet chaos starts. Next, the outer halos of stars feel the approach. Many of those stars already move quickly, just bound to the galaxy. As the partner draws near, a fraction are flung outward into the black between galaxies, never to return. Others are captured by the newcomer, folded into the other system's wide skirt. It is an exchange, a trading of lights across a gulf. Then the tidal pull grows. Gravity tugs a little harder on the near side than the far side, stretching both galaxies into long, thin tails. These tidal tails can reach for millions of light years, lovely and severe, like streamers left after a parade. They mark where giants met. Only later do the bright disks pass through one another. That meeting is not a smash. It is like two clouds interleaving. Individual stars almost never hit. The space between them is enormous, but gas clouds do feel the squeeze. Compressed gas collapses. Collapsed gas lights new stars. For a time, both galaxies blaze with fresh birth, a wave of bright blue clusters spreading across their arms. Astronomers call this phase a starburst. Here, size matters in a different way. Big galaxies have deep wells of gravity, so material pulled into tails is more likely to fall back. Smaller systems may shed gas and stars for good. Larger ones recycle. The Milky Way and Andromeda will fling out streamers, yes, But much of that material will rain inward again as the dance continues. And continue, it will large galaxies often loop around each other several times. 3 passes, 4, maybe 5. Each sweep strips more from the arms. Each swing drags the cores closer. Friction, both in gas and in the swarming stars, bleeds away orbital energy. The pair spirals inward. What remains at the end depends on the balance of masses. When 2 giants of similar weight merge, the neat spirals do not survive. Disk stars are stirred into random paths, and the final shape becomes a vast elliptical galaxy rounder, smoother, without tidy arms. Our future home has a nickname already: Milkometa. Picture hundreds of billions of stars and a mass measured in trillions of suns, a heavyweight by any local measure. Other changes follow. Each galaxy carries a supermassive black hole at its center. The Milky Way's hole weighs a few million suns. Andromeda's is far larger, roughly 1 billion suns. In time, those two will find each other. As they merge, they will send a deep ripple through space-time itself, gravitational waves strong enough to be felt across the universe by instruments that listen for such low, slow notes. After the first rush of star birth, the supply of cold gas will thin. Without fresh fuel, star formation will fade. The new galaxy will redden with age. As hot, young stars die off and older, cooler stars dominate. Over a few billion years, the blaze softens to a steady glow. This is not a distant movie trailer. Signs suggest the first, quiet stage may already be underway. If the halos of the Milky Way and Andromeda reach as far as we think, they may already overlap. In that sense, contact has begun, not with fireworks, but with a whisper. Scale sets the tempo and the ending. There's another balance to keep in mind. The mass we can see compared to the mass we feel through gravity. When we add up all the visible matter in the Milky Way, stars, gas, dust, planets, we get a few 100 billion suns worth. But if we weigh the galaxy by how fast things move around it, we need around 4 trillion suns. The gap is dark matter, the invisible mass that keeps the galaxy from flying apart. Yet even after dark matter is counted, a different shortage remains. Based on the cosmic ratio of ingredients, our galaxy should hold more normal matter baryons, like protons and neutrons, than we detect. This is the missing baryon problem. Where are they? One answer is that many baryons were blown out. Supernovae and winds from bright clusters can push gas outward for hundreds of thousands of light years. So can outbursts from active galactic centers. Over billions of years, a great deal of material may have been exhaled into the space around the galaxy, too thin to see easily. Another possibility is that the baryons hide in faint forms: cold, patchy gas, dim brown dwarfs, free-floating worlds that barely warm the dark. A third puts them in the in-between from the start, the intergalactic medium, an extremely thin mist spread over huge volumes. None of these answers excludes the others. The truth may hold parts of each. Recent observations lift a corner of the veil. Around many galaxies, including our own, X-ray telescopes see vast, hot halos of gas. This gas is ionized and thin, nearly invisible in ordinary light, but it contains real mass. Measure enough of it and a large fraction of the missing baryons reappears on the ledger. That feels like progress. But a heavier, wider Milky Way raises the bar. If the total mass sits near 4 trillion suns, the expected share of normal matter rises as well, and our counts still fall short. The larger the galaxy we draw, the more baryons we should find. Where are the rest? One thought is that the dark halo cradles huge stores of hot gas far out, hundreds of thousands of light years from the bright disk, so hot and so thin that even our best X-ray instruments barely whisper its presence. Another points to the circumgalactic medium, the in-between zone where gas cycles out and returns. Material pushed outward by explosions cools over time and drifts inward again, like weather in a slow climate. This reservoir is not fully inside or outside the galaxy. It is a threshold region, wide and dynamic. Instruments tuned to infrared light like those on the James Webb Space Telescope are beginning to sense warm gas that other surveys miss. Early hints suggest more mass lives in the outer halo than we once counted. To turn hints into clarity, we need more measurements and more time. All of this ties back to that slightly off-center balance point. A galaxy that is bigger and heavier than we thought will count different numbers of satellites, different speeds for stars at the edge, different amounts of gas in its halo. The center around which everything truly orbits moves a little as we learn to weigh all the pieces correctly. The first contact with our neighbor may already be underway in the dark. Tidal tales will one day sketch arcs across a changed sky. The missing matter we are looking for could be breathing in the warm outskirts now. The physics is steady, the picture grows, and with each careful revision of mass, of center, of border, the map of our home leans closer to the landscape the night has always held. Here is the quieter truth we live with. In our own galaxy, we cannot yet account for about half of the normal matter, the everyday stuff made of protons and neutrons that builds stars, planets, oceans, and you. We have a reasonable map of where the dark matter sits. Oddly, that has become the easy part. Regular matter keeps slipping away from our counts. A larger Milky Way makes the gap wider. More mass to explain, more places to hide, more questions to sit with in the dark. Somewhere, spread through the halo and the in-between, on the order of 400 billion suns worth of normal matter is waiting to be found. And our home is not an exception. Astronomy has a way of reminding us that what seems special is often simply common. If our galaxy is roughly twice as wide as the old diagrams, then many spirals are likely undercounted the same way. To test that idea, researchers turned to our neighbors, Andromeda, Triangulum, and other nearby spirals we can study in detail. They brought the newer tools: tracking of satellite galaxies, mapping of faint stellar streams, and careful accounting of dark matter halos. The results lined up. Each galaxy grew on the page, not by a hair, but by a lot, often 50% larger than the textbook numbers, sometimes nearly doubled. Andromeda gave the clearest example. Older measures put its width near 220,000 light years. Newer work pushes that to 300,000, maybe more, with its dark halo stretching much farther still. Triangulum, long listed near 60,000 light years, now approaches 100,000 in the deeper maps. Smaller spirals followed the same pattern. Objects like NGC 524 and NGC 2976 came back larger when the outer faint regions and the full halo were counted. The mistake was not sloppy, it was systematic. We measured the bright disks we could see and stopped there. We looked past the dim outskirts, underestimated the unseen scaffolding of mass, and drew borders where the starlight thinned rather than where gravity still held. Modern surveys change that. Wide fields capture galaxies edge to edge. Infrared eyes look through dust. Deeper exposures reveal sparse outer stars. Most of all, Satellites and streams act like test weights. Just as our Milky Way has companions, so do Andromeda and Triangulum. Follow their small galaxies, measure their orbits, and you learn how far the big gravities reach. Around Andromeda, we can literally see the evidence of meals in progress. Long streams wrapping around like pale ribbons, circling well beyond the bright disk. Those paths tell a simple story. The halo is broad, and the sphere of influence runs hundreds of thousands of light years. Count the halo fully, and spirals become enormous. The gaps between neighbors narrow. That shift ripples through the rest of the map. If galaxies are bigger, their halos overlap more often. Encounters become more frequent. The universe grows a little more crowded and more lively. Even the census changes. In the same volume of space, you count fewer separate galaxies. If each one is larger and claims more territory, models of how structure forms must be adjusted. Cluster histories and collision rates move in step. Rotation curves, the flat speed patterns seen in many spirals, also sit more comfortably in this larger frame, because extended halos naturally keep outer stars moving fast without flying away. Early looks at dwarfs suggest the same logic holds at small scales. Their halos reach beyond their faint stars as well. Ellipticals are harder to pin down, no clear disks, softer edges, but first passes hint that they, too, are roomier than their older figures. Put simply, for decades we drew what we could see and called it complete. The universe is asking us to redraw, gently and widely. Every spiral we check seems larger than the diagrams suggest. The census is being rewritten in a quieter key. Closer to home, our neighborhood feels the change. The local group, our small cluster anchored by three giants, the Milky Way, Andromeda, and Triangulum, does not shrink in matter, but it does shrink in concept. The space between big members is less neutral than we thought, because each galaxy's reach is farther. Territory we once labeled as between turns out to sit under one halo or another. The no man's land thins. Consider the distance to Andromeda, about 2.5 million light years. If our dark halo extends at least 250,000 light years, and Andromeda's does the same or more, that removes roughly 500,000 light years from the empty gap. Only about 2 million light years remain as truly neutral space, less if the halos prove larger. Some models even suggest the wispy outskirts already overlap, which would mean first contact has begun in the invisible dark, long before any bright disks touch. Shared borders change the traffic. The local group looks less like three islands with clear water between and more like three overlapping circles. Boundaries blur. Some dwarfs wander through zones claimed by more than one giant. The Magellanic Clouds are a telling case. For years, there were arguments about whether they were just passing through or truly bound. With a heavier Milky Way and a wider halo, the picture tilts toward bound companions caught for the long haul, their gas already trailing into the Magellanic Stream, their futures likely to end as part of our larger disk and halo. Between us and Andromeda, several dwarfs move in lanes where the poles compete. Over time, those small galaxies will be sorted, captured, or stripped, their stars added to one ledger or the other, and their streams written across the dim outskirts, like notes in a margin. All the while, the missing matter problem threads through the story. A heavier halo and a larger radius raise our expected share of normal matter. If the Milky Way truly weighs in near 4 trillion suns, then, by cosmic ratios, we should hold roughly 400 billion suns worth of baryons. We can count perhaps half of that directly in stars and cool gas. The rest seems to seep into places where our current tools are least sensitive. Hot, thin halos glowing weakly in X-rays, warm, diffuse gas in the circumgalactic medium, slow rivers of matter linking galaxies across the web. The James Webb Space Telescope and deep X-ray observatories are beginning to catch hints of these reservoirs, but the totals are not yet firm. The larger we draw the galaxy, the more carefully we must look for what belongs to it. The wider lesson is steady and calm. We did not overturn the laws that guide the sky. We refined the scales and extended the lines on the map. Galaxies wear halos broader than their glow. Spirals carry arms that split and fade and restart. Dwarfs drift where big poles overlap. The space between is less empty than the pictures in school once showed. Each correction, larger sizes, closer neighbors, missing matter placed in warmer, wider homes, moves our models closer to the landscape the night has always held. And while the numbers climb and the borders slide, the feeling is the same. A vast room, softly lit, with more structure than we first saw, and with patient gravity giving shape to it all. Out between the giants, some small galaxies move through shared tides. Which one do they belong to? In truth, they travel inside the combined pull of both the Milky Way and Andromeda. They feel gravity from more than one direction at once. As our two halos draw closer, these dwarfs will be caught in the middle, stretched and shredded into pale streams, their stars scattered like handfuls of salt on dark water. Triangulum faces a similar risk. It is the third largest member of our neighborhood, but only just on the order of 60 billion stars. Fresh measurements hint it may already be falling toward Andromeda. The gap between them is roughly 750,000 light-years. With larger halos, they are nearly touching. Triangulum may not remain an independent city of stars. It may already be a satellite of Andromeda in all but name. Redrawing borders changes labels more than head counts. The local group still holds about 80 galaxies, but some we once called independent shift into the satellite column, and others move the other way. As sizes and masses update, the group's center of mass, a balance point set by all the weight, slides a little in space. It sits somewhere between the Milky Way and Andromeda, likely a bit closer to Andromeda if it is the heavier partner. That point matters. Over very long times, orbits and infall paths for many members curve around it. It is the quiet hinge of our neighborhood's slow motion. Beyond our group, neighboring clusters wait behind their own veils. The sculptor group rests at a distance of about 12 million light-years. The Maffei group sits nearer, but hides behind the glow and dust of our disk. Each of these groups claims a zone of influence, and if galaxies are larger across the board, those zones swell. Gaps between groups shrink. Some astronomers now sketch the local group as wider than the old 10 million light-year rule of thumb, perhaps closer to 15 million because outer members roam farther than we realized, and the common pull stretches over more space. The larger picture changes too. Groups gather into superclusters. Depending on how you draw the lines, we sit within the Virgo supercluster or inside an even broader basin called Laniakea. If groups are larger, the map of these higher tiers reorganizes. Ridgelines move, basins widen, flows between them bend. The hierarchy shifts at every level. Underneath all the cartography is a simple, strange truth. Boundaries are our invention. Nature prefers gradients, not walls. Galaxies blur into each other's halos and share the same long fields of gravity. The local group is less a box of separate things and more a wide bowl of matter with bright knots we call galaxies. We draw lines to talk and to measure, and then the universe quietly reminds us that the lines are only chalk on a moving tide. Now fold your attention back to our own home. The star count has doubled. The Milky Way likely holds around 400 billion stars, perhaps more. Numbers that large slip past the mind, so hold them gently. If you counted one star each second without sleep, it would take more than 12,700 years to finish, and you would still leave billions uncounted. Compare it to people. There are a little over 8 billion humans on Earth. You would need about 50 Earths, all fully populated, to match the stars in our galaxy. Older estimates near 200 billion were not careless. They were based on small samples. Astronomers counted stars in regions they could see well, then scaled up by volume. The scale factor was the problem. Double a galaxy's radius and the volume grows by 8. The outer reaches are sparse, yes, but not empty. Add up all those quiet outskirts and the total swells. Most of the extra lies in small red dwarfs, cool, dim stars that live for trillions of years. They make up roughly 70% of all stars, yet contribute little light. A billion red dwarfs can hide in a space that looks almost dark to the eye. Deeper surveys reveal more of them in the outer halo than we once counted. Hundreds of millions moving on long, tilted orbits, far from the bright disk. Many are ancient and metal poor, fossils from the galaxy's earliest days. Others were born elsewhere. Every time the Milky Way swallowed a smaller galaxy, it kept the stars. Those immigrants now trace wide paths across our sky. The Sagittarius dwarf alone has given us tens of millions of stars. Its main stream likely carries around 100 million. They are part of us now, folded into our census. 400 billion stars means 400 billion chances to build worlds. Not every star has planets, but many do, perhaps most. A careful, conservative guess says around 60% host at least one. That is 240 billion planets at minimum. How many could be friendly to water on the surface? The estimates vary, so let's keep it cautious and simple. If even 1% lie in that just right zone, you still have about 2.4 billion potentially habitable worlds in this one galaxy. If life is painfully rare, say it sparks on only 1 in a million of those, there could still be around 2,400 living worlds scattered through our halo and disk. If minds like ours are rarer, still 1 in a billion planets, there may still be 2 or 3 civilizations out there, somewhere under the same wide halo. The Drake equation, a simple way to think through such numbers, would nudge upward on many of its steps with a larger galaxy. More stars, more planets, more time and places for chemistry to try itself. None of this guarantees company. It simply opens the door a little wider, and the larger our maps grow, the more they invite a careful question. What is hiding in the dim margins we have yet to search well? The outer halo is a frontier of quiet surprises, rogue planets that drift without suns, failed stars that never lit truly, small black holes and neutron stars that only reveal themselves by their pull, and, likely, classes of objects we have not yet named because we have not yet learned how to look for them. All of it, the shifting labels of dwarfs caught between giants, the widened borders of groups and superclusters. The doubled star count and the swelled ranks of planets points to the same calm conclusion. Our universe is larger, denser, and more connected than the old diagrams allowed. The night is not empty between the bright streets. It is a wide, shared field with long, patient structures running through it, and we are still adding up what that means. Star by star, stream by stream, breath by steady breath. Every star carries a quiet biography, a cradle in a collapsing cloud, a long middle age burning hydrogen, and a final act as a white dwarf, a neutron star, or a black hole. 400 billion stories are unfolding at once across the Milky Way. Our sun is only one voice in that choir, steady, ordinary, a single note among hundreds of billions. The count has swelled, and with it a small paradox. A galaxy this crowded can still feel lonely. So many stars, so many worlds, so many chances, and yet no clear hello from beyond. The larger tally does not promise company, but it does tilt the odds. A bigger Milky Way changes the search. Begin with the idea of a habitable zone, the ring around a star where a world might keep liquid water on its surface. The ring shifts with the star's size and temperature. Around red dwarfs, it hugs close. Around sun-like stars, it sits near our own orbit. Around giants, it drifts farther out. Count one zone for each star, and you already have hundreds of billions of potential rings to inspect. We do not need all of them to carry planets, only some. Space telescopes like Kepler taught us that planets are common. Most stars appear to host at least one world. Many host several. If we stay cautious and say 6 out of 10 stars hold planets, that gives roughly 240 billion planetary systems. If only a tenth of those systems place a world in the gentle band of warmth, that is on the order of 24 billion candidates for liquid water, twice what we would have guessed before the map grew. Habitable does not mean inhabited. A planet can carry oceans and clouds and still be sterile. Life needs more than water. The right chemistry, steady energy, long spans of time. We do not know how often the spark catches. We have a sample size of 1. To keep the thought grounded, imagine life is modestly rare. 1 in 1,000 habitable worlds stirs. That still leaves something like 24 million living planets in our galaxy, places where chemistry learned to copy itself, where cells divide and adapt and endure. Most would host simple life. On Earth, microbes ruled for billions of years before anything complex walked. Intelligence seems rarer still. If minds like ours arise on 1 in a million living worlds, the tally would be on the order of a few dozen thinking species across the Milky Way. The numbers lean and wobble, but the direction is clear. When the stage doubles, the possibilities widen. With more possibilities comes an older question, sharpened by scale. Where is everybody? No probes in our skies, no signals we can be sure of, no clear artifacts hanging between the stars. Some suggest a great filter, a barrier that most worlds never pass. Perhaps it sits behind us, and life itself is the hard part. Perhaps it waits ahead, and complex societies often undo themselves. Others argue intelligence is rarer than our simple fractions allow. The uncomfortable thought remains that we might be alone, at least locally, a single civilization speaking into a quiet room. There is a gentler reading. Doubling the stars doubles both the search space and the number of potential senders. Projects that listen for narrowband radio or fast optical flashes now have more targets worth their patience. SETI looks in thin slices of the sky and narrow lanes of frequency. A larger galaxy gives more lanes to try and more reasons to keep the receivers humming. Meanwhile, new instruments look for life by its byproducts. When starlight passes through a distant planet's air, certain molecules, oxygen, methane, ozone, other tracers can leave fingerprints in the spectrum. The James Webb Space Telescope has begun work in that direction. Others will follow, tuned to catch faint hints from small, quiet worlds. Each candidate we add is another coin placed on the table. More coins do not guarantee a win. They make a win less surprising. Stand in your mind at the galaxy's edge and look outward. You will not find a cliff. The Milky Way does not end. It fades. Star counts fall with distance from the center, gently at first and then more quickly, but not to a clean zero. Dark matter thins too, a slow diminuendo rather than a hard stop. Where does our galaxy become not our galaxy? The universe refuses a crisp answer. Earth's air offers a friendlier image. Pressure drops with height, from dense at sea level to thin at the edge of space. Yet atoms and ions still drift thousands of miles up. We draw lines, the Kármán line, the top of the stratosphere, because names help us work. Nature, meanwhile, keeps the gradient. So it is with stars. The crowded central regions pack extraordinary numbers into small volumes. Out near our sun, the density is far lower. Farther out still, stars are sparse, separated by great dark stretches, and yet not entirely gone. A few wanderers drift in the deep halo, some born here, some thrown there by past encounters. A handful have been kicked loose so hard that they travel between galaxies, no longer truly bound to any one home. Whether such loners count as Milky Way stars depends on the rule you choose. The dark halo complicates the same question. It extends far beyond any bright disk, but it fades so slowly that any edge is a choice rather than a discovery. All of this, the number of stars, the breadth of halos, the softness of borders, flows back into the search for life and company. A larger galaxy means more rooms to check, more quiet outskirts where small red dwarfs keep their tiny warm rings, more chances for ancient worlds to carry on undisturbed. It also means more distance for any signal to cross and more time for messages to miss each other in the dark. The paradox remains. A crowded galaxy can still be quiet at a single place and time. Yet the odds moved, and with them, a small human feeling, hope, gained weight. Somewhere beneath the same broad halo, perhaps on a tide-washed world around a dim star, life may have learned the trick of listening. Perhaps it looks up, notices its own sky growing larger as its maps improve, and wonders the same things we do. The numbers do not comfort on their own. The story they hint at can. In a galaxy with 400 billion stars, a careful search takes patience. Patience is something the universe has in great supply, and tonight, under its steady dark, so do you. The halo stretches far past the bright streets of the disk. How far depends on where you decide to stop counting. Many models place a comfortable reach at roughly 250,000 light-years. Others extend it to 400,000, and some trace a faint breath outward towards 600,000. Past that, the density thins until it blends with the background of space. Dark matter is not a local feature. It pervades everything, even the rooms between galaxies. The handover from Milky Way to not quite Milky Way is smooth, a slow fading rather than a wall. Gas makes the border softer still. Our galaxy exhales. Supernovae and clustered young stars drive winds that push material outward for hundreds of thousands of light years before it disperses. Is that gas ours? It was born here, and much of it will drift back over long cycles, raining down to feed new stars. But for now, it lives beyond any tidy boundary. The Magellanic Stream shows what this in-between looks like. Gas torn from the Magellanic Clouds trails across the sky for something like 600,000 light years. It is no longer theirs, and not yet ours. It hangs in limbo, a ribbon in transitional space. Companions blur things too. Satellite galaxies orbit within our pull, and yet we label them as separate because they carry their own stars and shapes. They are bound to us and will likely merge with us, but until then they sit on both sides of the definition. The virial radius tries to offer a clean rule. Draw the sphere inside which gravity keeps a family moving together, and call that the galaxy. For the Milky Way, many studies place this near 250,000 light years. Others choose a rounder 200,000. Useful, but not absolute. Outside the line, gravity does not switch off. Its influence weakens with distance, yet never vanishes. Light, too, carries our signature out forever. Every star that ever shone here sent photons in all directions. Those packets of light move on without end, announcing our presence to whatever listens far away. In that gentle sense, the Milky Way's reach is unbounded. Measuring the galaxy, then, is as much a choice as it is a detection. One mapmaker picks a threshold in star density. Another traces the dark matter until it falls below a chosen level. A third follows where satellites remain in orbit. Each method returns a size. None is wrong, none is perfectly right. The universe prefers gradients. We lay our rulers across them so we can compare notes. Under those soft borders, a harder truth has shaped us. The Milky Way grew by eating. Over billions of years, hundreds of smaller galaxies drifted inward, were pulled apart, and were folded into the whole. Streams of stars, long, thin, and pale, wrap around us as gentle evidence. Each is the remnant of a companion that came too close. The ribbons circle for ages and eventually disperse into the general halo like salt dissolving in water. One such meal is happening now. The Sagittarius dwarf, carrying on the order of a few 100 million stars, is being unspooled across our sky. Over the next billion years, those stars will scatter through our halo. Give it 2 billion, and the dwarf itself will vanish as anything but a pattern in the motions, a ghost that only careful data can see. We have fed before, and the older feasts left deeper marks. About 10 billion years ago, a substantial intruder, Gaia Enceladus, fell in. It carried perhaps a quarter of the Milky Way's mass at the time. The merger was violent, the kind that shakes a disk and seeds a halo. We absorbed the intruder, and billions of its stars now orbit here. We know them by their paths. Many move against the general spin, on tilted, elongated orbits. We know them by their chemistry, different balances of heavy elements that betray a history written in another place. The Gaia spacecraft made these differences clear, measuring positions and motions with the steadiness needed to tease out old stories from the present sky. Earlier still, something even larger may have struck an event some researchers call Kraken, roughly 11 billion years ago. Perhaps half our mass at that time. That encounter likely reshaped the early Milky Way, triggered intense star formation, and helped build the body of the disk we cross today. Its remains are harder to tease out because time has mixed them thoroughly, but the signature lingers in the numbers and the motions. Other names dot the ledger: the Sequoia event, the Helmi streams, and Omega Centauri, a massive globular cluster that may be the stripped core of a once independent galaxy. Each points to the same quiet pattern. We became large by gathering others. Picture the numbers stepping through time. 10 billion years ago, we may have held something like 50 billion stars, a respectable spiral, not yet a giant. Then came Kraken, and our mass doubled. Gaia Enceladus added more. Dozens upon dozens of smaller dwarfs trickled in, each leaving streams, clusters, and a dusting of stars that sank into the halo. The process is not done. The Magellanic clouds circle closer on wide loops. Their gas already paints the sky in the Magellanic Stream, a preface to their future. Sagittarius is mid-course in its own unraveling. Small companions that venture too near will, over time, become part of our light. Farther ahead lies the patient meeting with Andromeda. That will not be a single bite, but a long folding together, the last grand meal that ends the age of spirals here and leaves a vast elliptical in their place. By then, the borders we argue over today will have been redrawn by motion and time. Streams that now look like delicate handwriting across the halo will be stirred into a broad, smooth glow. The galaxy we call ours will still be here, present in everything that results, but changed as living things change. Hold the thought that all of this soft edges, quiet cannibalism, ribbons of stars, sits under the same unhurried night, The halo fades rather than stops. Winds carry gas out and bring it back. Companions drift in, leave trails, and become part of the whole. What we call the Milky Way is a region, a process, and a history at once. A wide, invisible frame with a luminous heart, growing by slow gatherings and shaped by gentle gradients that never quite end. Big galaxies grow by eating. Once a system becomes heavy enough, its reach extends, and reach begets more reach. Gravity pulls in a small companion, the meal adds mass. The larger mass pulls in the next one. It is a feedback loop written in stars. Dwarf galaxies live on the hard side of that loop. They circle as prey, nibbled by tides, stripped by close passes, and more often than not folded into their larger neighbors. Only a few strays survive far from any hungry giant. The Milky Way built its standing in the local group by gathering whatever drifted close. Yet nothing we ate truly vanished. Those stars still burn. They simply orbit under a new flag. In that quiet way, our galaxy is not a single thing but a collective, an empire made from the remnants of many smaller cities of light. The iron in your blood and the carbon in your cells were forged in ancient stars, some likely born in galaxies with their own histories, Gaia Enceladus among them, before their ashes mixed with ours. We are built from imported matter, immigrants, all of us, in a place where borders were erased by gravity long ago. We grew through encounters, mergers, and slow cannibalism, and we are still growing. Saying this out loud is less about drama and more about honesty. Scientists do not resist being wrong out of pride. They resist because being wrong means rebuilding the scaffolding, redoing sums, rewriting models, admitting that a comfortable picture needs to change. The James Webb Space Telescope pressed that point with a steady hand. Launched in December 2021, Webb is a deep, cool eye tuned to infrared light far more sensitive than any space telescope before it in that band. Infrared gets through dust that blocks ordinary starlight. With that gift, Webb looked into places that were hazy or hidden, the dense lanes near the galactic center, the far side of our disk, the thick clouds where stars are born. What appeared was more than we sketched, more structure, more faint stars, more complexity in regions we once called empty. Out in the outskirts, where maps faded to gray, Webb saw lonely red dwarfs and sparse clusters we had not counted. The view of our companions sharpened too. Webb resolved individual stars and distant dwarf galaxies, weighed their ages and elements, and pinned down their distances with care. Each measurement tightened our picture of the Milky Way's pull, and the tighter that picture became, the larger the map grew. The most persuasive tracers were the long, thin, stellar streams, the fossils of past meals. Webb followed these ribbons farther from the center than past surveys could manage 200,000 light years and beyond, some near 250,000. Streams that long should not exist around a small galaxy. Their presence made the old size difficult to defend. Then came the weight. Light from background galaxies bends as it passes through our extended mass, a quiet prediction of general relativity. Webb's precision let astronomers measure that gentle bending with new confidence. From those arcs and smudges, you can infer how much mass sits in the way. The totals pointed upward, on the order of 4 trillion solar masses for the Milky Way, perhaps more, about triple the older, comfortable figure. Other methods, satellite motions, stream shapes, wide field maps, nodded in the same direction. Debate followed, as it should. Some held to the earlier sums. Others accepted the new ledger at once. Paper by paper, the balance tipped. The consensus shifted. We live in a bigger, heavier, more intricate galaxy than our textbooks described. Webb did not stop at our front porch. It turned to Andromeda, to Triangulum, and to spirals far beyond, and found the same pattern: broader reaches, fatter halos, longer streams. The bias was not local. It was baked into how we used to measure. New data forced a rework. Theories of how galaxies grow, catalogs used to set distances, even pieces of cosmology that rely on honest head counts and weights. This is the slow courage of science. Instruments change, data improves, models give way. Comfort is not the goal. Truth is, all of this folds back into the largest unsolved piece of the puzzle: dark energy. That name stands in for whatever is driving the universe's expansion to accelerate a push that makes space itself stretch faster over time. We can measure that acceleration by watching distant supernovae fade, and those measurements are consistent. To understand the push, we first need to know the pull, how much matter exists and how it is spread. If galaxies everywhere are larger and heavier, then the universe contains more matter than our older ledgers allowed. More matter means more gravity, which should tug harder and slow the expansion a bit more than we thought. But the observed expansion rate has not budged. It still accelerates at the measured pace. Two paths appear. Either dark energy is stronger than we assume to balance the extra pull, or our simple picture that dark energy is the same everywhere and always needs softening. The standard model of cosmology treats dark energy like a constant property of space, the same in every corner. Heavier galaxies make that assumption harder to keep. Perhaps the push varies with time or place. Perhaps gravity itself behaves a shade differently on the largest scales that our equations describe. There are careful, competing ideas: modified gravity, dark energy whose strength changes slowly, patterns in the universe's structure that bias our measurements. A roomier cosmos gives those ideas space to be tested without abandoning what already works. And then there is a riddle that sits like a pebble in the shoe: the coincidence that dark energy and dark matter contribute similar orders of magnitude to the universe's total budget, roughly 70% for dark energy, about a quarter for dark matter, a few percent for normal matter. If we raise the matter side of the ledger by counting halos to their full extent, the balance must be retuned. Why these proportions? Now, in our era, a larger tally does not answer that question. It makes the question sharper. Through it all, the tone stays the same: quiet, methodical, willing to be surprised. Our galaxy grew by gatherings and meals. Its edges fade rather than end. Webb's infrared vision widened our sight at home as much as it did in the deep past. Bigger masses ripple through models of groups, clusters, and the whole expanding web. Dark energy feels the pull of those changes and pushes back, as it always has, in our equations and in the sky. The numbers move, the night remains steady, and we keep adjusting our rulers, letting the map lean a little closer to the landscape that was always there. Why those neat ratios at all? Why about 70% dark energy, roughly a quarter dark matter, and a small slice of normal stuff? Why not 90-10 or 50-50? The match feels suspicious. If galaxies carry more dark matter than we counted, the coincidence looks worse. You would need even more dark energy to keep the same balance, or you accept that the balance itself has shifted with better measurements. Either way, the riddle stands. Some cosmologists suggest it is not a true coincidence at all. Perhaps dark matter and dark energy are related, two faces of a deeper thing we do not yet see. If heavy halos are larger, maybe they also stir or couple to dark energy in their neighborhoods in ways our current equations smooth over. Testing this is hard. Dark energy does not glow or clump. It looks uniform and steady as far as we can tell. You cannot point a telescope at it. You can only watch what it does to the expansion of space. Those wider galaxies also reach into another cosmic yardstick: baryon acoustic oscillations, the faint ripples in how galaxies spread across the universe, frozen sound waves from the early plasma. We use the spacing between ripples as a standard ruler to set distances and, from there, to weigh dark energy. But ripple spacing depends on clustering: how many galaxies there are, how heavy they are, how they group on large scales. Enlarge the halos and the clustering shifts. The ruler needs a small tweak, distances change a little, and dark energy estimates move with them. Close to home, the Hubble tension gets pulled into the conversation. Local measurements that rely on nearby galaxies and supernovae give one expansion rate. The early universe picture painted by the cosmic microwave background gives another. They disagree by around 9%, which is large in a field that lives on careful error bars. Bigger galaxies press more on the local side than on the early universe side. Calibrations that depend on the structure of nearby galaxies could slide, perhaps easing the tension, perhaps tightening it. For now, the jury is still out. Through all this, the basic model of the cosmos, the working recipe with dark matter, dark energy, and ordinary matter still fits a staggering range of facts over 13 billion years. But it has dials we set by measurement, not by first principles. If those inputs shift, the whole recipe trembles. Heavier, roomier galaxies make the table shake. Not enough to topple it, not yet, but enough to make everyone check the legs. The universe is accelerating. That part is firm. Why it accelerates, and exactly how strong the push of dark energy must be, just became murkier. So we return to our own address, 200,000 light years. That is the best working size for the Milky Way today, perhaps edging toward 250,000 depending on how you define the edge. It is not final. It is simply the most honest number we can defend now. What is solid is that the old 100,000 light-year picture is too small. Independent lines of evidence all point outward stellar streams arcing far past the bright disk, satellite galaxies orbiting at greater distances than expected, maps of the dark halo, and gentle bends in background light that reveal our mass through gravitational lensing. Together, they make a coherent shape. 200,000 light-years fits the orbits, matches the streams, and sits well with halo models. It is reasonable, careful, probably close, but not the last word. What are we missing? We need clearer maps of the dark halo far from the center. Many models still extrapolate from the inner regions and assume a smooth fade. Direct measures in the outskirts are thin. Wider, Deeper lensing surveys would help. More known satellites would refine the gravitational field. Simulations tuned to those orbits would test the totals. We need to see fainter stars at greater distances. The outer halo is salted with dim red dwarfs spread across huge volumes. Many are still below our limits. Each step in sensitivity adds points to the map and nudges the line outward. We need better distances to the long, pale streams. Is a ribbon 150,000 light years out or 200,000? Parallax from Gaia improves the inner ranges, but the far reaches will need new tricks. We need to understand our galaxy's winds, how hot gas flows out, how far it travels, how and when it falls back. Winds shift mass estimates and blur boundaries. We need to find the missing satellites that simulations predict. Are they simply too faint, or are they parked so far out that we have not looked deeply enough yet? The Magellanic Clouds carry their own question. Forever bound or long passing arc? Pin the orbits, and the Milky Way's true mass tightens. And we need to define, with care, where we end and Andromeda begins. If the halos already mingle, that boundary is not just philosophical. It sets the clock for when our long meeting truly starts. New tools are coming to help. A wide field space surveyor will scan huge swaths of sky at depth, netting faint satellites, far streams, and soft lensing signals across broad fields. On the ground, a giant mirror more than 100 feet across will split crowded stars in nearby dwarfs and time their motion with exquisite care. With each pass, the uncertainty shrinks. 200,000 light years may become 220,000, or 180,000, or 250,000. The number will move. Confidence will grow. Perfection will remain out of reach, because edges in nature are gradients, not walls. What this tells you is simple and humbling. We live inside a thing so large that we have to measure it from within, with limited sightlines and patient inference. Today's answer is our best effort. Tomorrow's will be better. The galaxy keeps revealing itself. One stream traced, one satellite weighed, one soft bend in distant light understood. And every improvement extends the roof over our heads. So hold the picture gently. Our home is larger than we thought, roughly twice the width, roughly triple the mass, about 400 billion stars, an uncounted world still forming, still merging, still hiding structure in its faint outskirts. The deeper mystery of the universe, the push of dark energy, the pull of dark matter did not get smaller as our map grew. It deepened, the way the sea deepens as you step off the shelf. The final number for our size is not in hand. It may never be final, but we are closer than we were, and we keep moving one measurement at a time, one careful correction at a time, breathing with the quiet wheel of the Milky Way as it turns. For now, call it about 200,000 light years across, and let the night go on, refining the rest. Let the figures and maps rest now. We have drawn a shape for our home, a wide, gentle wheel without sharp edges, and we know it will shift again in the morning. That is enough. You can feel the quiet truth of it. Gravity holding, light traveling, the halo fading into a softer dark. The questions do not rush. They wait like stars beyond the roofline. The room dims another shade. The last bits of day loosen from your shoulders. Somewhere, far outside the window of sleep, streams of old starlight wrap the galaxy in slow ribbons, and the balance point we chased settles for the night. We live inside a story still being measured, one careful line at a time. For now, the map is wide, the laws are steady, and your breathing can match their calm. Inhale and picture the spiral as a slow tide. Exhale and let the numbers drift until they are only dust on a long, dark current. The lamps of 100 billion suns turn to a soft haze. The edges blur. The wheel keeps turning without you having to hold it. If there is an answer, it can arrive later. For this moment, the night is large enough. Let the light thin to hush. The stars pass like quiet boats, and your breath fold into the dark. Keep floating. The story continues, and you are already in it.